Hello, my name is Darien Morphew. Today I'm going to be talking about the Journal Club presentation paper that I chose, which is over the topic of unsupervised learning. So the paper that I chose is somewhat adjacent and related to the research that I do with shape memory alloys and elastochloric refrigeration. And so the title of this paper is Combinatorial Synthesis and High-Throughput Characterization of Microstructure and Phase Transformation in Nickel, Titanium, Copper, Vanadium, Quaternary Thin Film Library. And this paper was published in the Journal of Engineering and written by a group out of Maryland University in their Department of Material Science and Engineering, with the lead author being Naila Al-Hassan. All the authors listed here below. And just to give an overview and scope of this paper is they utilized a single thin film library of this quaternary alloy and analyzed its shape memory alloy effects, as well as the different crystal structures seen across the various compositions, and then also some important characteristics of applications that include hysteresis width, which is very important in something like elastochloric refrigeration. And so I want to talk about first just a scope and just an overview of what the authors did in this paper. And so first, in their methods, what they did, they synthesized a nickel, titanium, copper, vanadium thin film using magnetron co-sputtering. Results are kind of visualized here below, where you can see the four different atomic percents over the wafer. So this was on a single silicon wafer, and they basically produced just a gradient of compositions of each atom. And in doing so, if you like zoom in with a fine resolution, you can see they identify 177 different total regions, but it was 177 different regions of composition space. And so in doing this, they were able to create a single wafer, and they basically looked at 177 different type of alloy compositions. And so they also characterized the microstructure and phase transformation properties. And one way they did that for the phase transformation properties anyways, is they were looking at transformation temperatures, such as austenite start, austenite finish, martensite start, martensite finish, which are the two phases relevant and present in these shape memory alloys. And basically, you can see here in this image below of each identified composition on the wafer. They took resistance measurements to find these phase transformation properties. And so they did a 4-point probe method where they put the 4 points and measured resistance across each small composition and moved these probes all around the wafer to get these resistance profiles for each composition. And these resistance measurements are an indirect measurement of the phase transformation. So you're not actually measuring, percent of martensite phase transformation, percent of martensite. But the resistance measurements are an indirect measure of that. And so you can see on this right-hand side of the wafer, which is where the shape memory effect was actually visualized, you can see these U shapes that are reversible with some hysteresis are typically identified as the shape memory effect, which is what these authors were looking at basically for this quaternary system. And so they also characterized the microstructure, and they did this by using WDS, or wavelength dispersive spectroscopy. And this basically confirmed and identified the compositions at each region. So all of their dots you see in this image in the back, they used WDS to find those. And then they also used synchrotron XRD. And they did this to basically obtain detailed information about the crystal structure of these different compositions. And we'll get into this in the next slide of how they used machine learning to process these results. But basically using this XRD data, they were able to identify phases, different phases present, and basically the phase boundaries along this wafer. And then they used these resistance measurements and these, the characteristic temperature hysteresis width and these resistance curves, and they could relate these crystal structures and, of course, the compositions to the desirable, small hysteresis widths that also showed these shape memory effects, as you can see on, like I mentioned earlier, these U shapes on the right-hand side of the wafer. And so what they were trying to do is they tried to identify compositions that not only show the shape memory effect that I talked about, but also show low thermal hysteresis, because the second fact is what's important for applications such as elastocaloric cooling. It's very important to have a low thermal hysteresis, and of course you must have a shape memory effect as well. And so how they used unsupervised machine learning, you can see in this top left figure, figure A, is their XRD data. And so they basically had this XRD diffraction data for 177 different compositions, which is a lot of data to try and analyze. And so what they did, they used an in-house unsupervised learning method, but they used unsupervised learning to cluster this data to relate data sets that were similar, had similar diffraction peaks and intensities, so they could basically map out total phases in the wafer shown in the previous slides. And so they used unsupervised learning, and they used the Pearson coefficient correlation, which is seen down here by this equation. And all that is it's just a statistical measure that evaluates the linear relationship between two sets of data. And in the context of XRD results, it just allowed them to basically cluster compositions that had similar XRD data, is as simple as I can put it. But this was extremely useful because they could identify, sort of global phase boundaries along the wafer itself, and which allowed them to group these compositions by their similar phases. And of course, like I said, the key was creating these phase boundaries so they could focus on regions in the wafer that not only had favorable phases that allowed for shape memory effect, but also had low thermal hysteresis. And so in general, what this did was this just accelerated the discovery process for ideal, in this specific quaternary alloy, identified ideal compositions for the shape memory effect, and also the shape memory effect composition that had low thermal hysteresis. And this is sort of their clustering result in this top right figure you can see here, where this it's called a hierarchical clustering technique, but basically they start in the first iteration assuming nothing is clustered, each individual XRD data is its own cluster, and then from there they can start to cluster through different iterations and define some ideal cutoff point, which is what they did to identify the global phases. And so in the end, the new information that was learned from this paper and research were, first, in this quaternary system, this nickel, titanium, copper, vanadium system, they identified 32 compositions with shape memory effects. And instead of testing these, like synthesizing one film itself and then making another film at a different composition and slowly testing this, by using their magnetron co-sputtering technique to basically create that gradient of compositions and identify each composition, they were able to identify 32 compositions with shape memory effects, and while doing it being a high throughput paper, meaning they were able to do this quickly compared to other techniques. But another key feature and important feature is they also identified 5 compositions that showed 0 or near 0 thermal hysteresis, seen in this figure on the right here, which is very important for applications like elastocaloric cooling, because hysteresis is basically just heat loss in the system. And so to make these devices and refrigeration cycles more efficient, we want to reduce hysteresis as much as possible. But essentially, by using machine learning, the authors were able to quickly map out structural phases on their wafer, identify the phase boundaries across the compositional space, and then this allowed for a accelerated discovery process of materials that showed not only the desirable shape memory effect, but also low thermal hysteresis. And that is all. Thank you.